This video focuses on situations where a block has been stacked on top of another block, and we are trying to look at the motion of those blocks, and we're taking into account the friction, static and kinetic in the system. They can be pretty messy. So before we dive into a couple examples, let's talk through some strategies that we're going to want to keep in mind. When I think about these problems that involve stacked blocks, there's sort of three types of questions that we might be asked, three things we might consider. For one thing, we may know that the blocks do not slip, and maybe we're being asked to find an unknown mass or a coefficient of static friction or something like that. In these cases, go ahead and start the problem like you would a problem that didn't have stacked blocks. Okay, find the system acceleration by using F equals ma. And then once you have that value of acceleration, then focus in on one or the other block and use that to find that unknown. If you're told that the blocks do slip, okay, if you know that information, then you can't find a system acceleration. The whole idea is that blocks are moving separately, and so you can't use the same A in the entire problem. And so what you need to do instead is just focus individually on each of the blocks. Most likely you're going to have to look at two or more parts of the system and then somehow connect them together. Now, the real messy question is if you're not told whether or not the blocks slip. And so in that case, you have to first answer that question so that you know which of these other two strategies to use. And so what you want to do is assume that they do not slip. Okay, make that assumption right from the beginning, and then you're going to check that out and see if it actually works with the information given. So go ahead and you find the system acceleration, and you use that then on one of the individual blocks, and you check to see if maybe static friction is sufficient to hold things in place. But again, these are easier understood by looking at an example, so let's go ahead and get into those problems. All right, so here we have a block stacked on top of another block, and then we're pulling on the system from the bottom, just like the initial picture looked like. Let's go ahead and get some things labeled. Forces are of course the key here. So we have 60 newtons of applied force, so I'll put that in here. There's some contact between the surfaces, so there's definitely weight and normal force. I'm not going to put that in my picture right now. We'll think about it in a few minutes. But let's look at contacts. So there's contact at the bottom here with the table, and so there's going to be friction. And so since the object is definitely moving to the right, there's going to have to be friction to the left. Okay, and there's going to be two frictional forces, so I'm going to call this F sub F1. And that's a kinetic friction, so we're going to be using that 0.1 to calculate that. In between the blocks, because they don't slip, the friction there is static. And so I'm going to include it in my pictures because we're going to need it later. But for this first step, we will see that it's internal and it can be ignored for the moment. But if you think about this, if there was no friction and you pulled that big block to the right, the top block would slide to the left in reference to the larger block. And so there has to be some sort of static friction pointing the opposite way, so to the right, keeping that from happening. Okay, and so that's our second frictional force exerted or applied to the top block pointing to the right. But because these two blocks are both important, because the bottom surface isn't just a table, it's a block, I'm going to include the kind of counterpart to that due to Newton's third law. So if the bottom block exerts a rightward force on the top block exerts a leftward force on the bottom block. Okay, so I have all these forces here. Now, the first thing I'm going to do, though, is I'm going to look at the system. F is equal to ma. Make sure I write that down. But when I look at the system and I include all these forces, those two blue forces are equal and opposite, so they cancel each other out for the system equation. So I don't even need to write them down. They are internal forces. My frictional force is going to be calculated by taking a mu times a normal force because it is kinetic. So I can put that value in right away. And then I can put some specific value. So 60 minus, and then I use the kinetic value of mu, so 0.1. Now my normal force, for here I want to be thinking about how this friction is right here at the bottom of the big block. So everything above that dark red line impacts the friction. So the 4 kilogram block and the 8 kilogram block, their weights are both pushing down on the surface, and so the surface has to exert a force up to balance it. So my normal force here is 120 newtons, and I'm looking at the whole system here, so my mass in this equation is going to be 12. It's going to be the total. Do a little algebra, and we would find that our acceleration is 4 meters per second squared. All right, so that's definitely what's happening because the blocks don't slip. So let's use that to find out how much friction we are going to need in order to keep this top block in place. So if I switch now to just the top block, okay, the top block needs some sort of frictional force, this what I'm calling F sub F2, in order to hold it in place. And it's going to have to equal its mass times the acceleration of the system. So I'm going to need 16 newtons of friction in order to keep this in place. Now the actual frictional force is less than or equal to the maximum value of friction here. Okay, but I'm going to be looking at this. I want this minimum value of the coefficient of friction. I want to be just at the point where it's almost going to start to slip. So I'm going to go ahead and think about this as an equality instead, and go ahead and find out what that mu value would need to be, what the minimum value. So I'm going to call my frictional force 16. My normal force, now this is different. The normal force is only due to the 4 kilogram object because I'm looking at the friction right here in between the blocks, and so it's only everything above that blue line that matters. So my normal force is 4 times 10 or 40 newtons, and so my mu sub s as a minimum has to be at least 0.4 as that value. It can be bigger, but that's the minimum amount, otherwise I won't have enough friction. All right, let's take a look now at a situation where we don't know whether this slips or not and see what we have to do there. All right, so now we have a block on top of a block, but I've added in a pulley just for some extra practice, and we know now that the coefficient of friction is that 0.4 that we found, and the coefficient of that was static, and the coefficient of kinetic friction everywhere it applies is 0.1. And so we want to find out, first of all, whether or not this top block does actually slip. So this is our 2 kilogram block, and we've got a 4 kilogram, so I changed the numbers a little bit here so they work out nice. And then we've got 12 kilograms hanging over the edge. All right, so let's take a look here. We don't know whether this slips or not. So again, what we're going to do is we're going to assume that it doesn't slip. Okay, so that's just kind of a checking here. We're going to assume that it does not slip. No slip. Okay, so in that case, then we can go ahead and see if that's what that system equation leads to. Okay, so if I look at the system, then I have this force, this weight pulling down 120 newtons. Now I do have weights pulling down here, but they are perpendicular to the motion, and so they don't affect that horizontal motion of those blocks. So I'm not going to worry about that with the net force. I have tension pulling here, and I have tension pulling here. Those are the same tensions if it's ideal, but again, those are internal. Not going to worry about that right now. The only other force I need to worry about here is friction right here. Okay, so there's a frictional force at that bottom surface. You know, there's friction at these surfaces too, but again, I'm not going to worry about those because I'm assuming right now that it doesn't slip. So really all I got to deal with is I've got the weight pulling down 120, and I've got some friction, mu times the normal force, that is working against the motion. Okay, and again, I'm looking at the system here. I've taken into account everything as I wrote this equation. So just like we did last time, we're going to use the kinetic mu, and we're going to go ahead and use the normal force of everything, all the weight above the surface is exerted downward on the surface, and so the normal force would have to equal that to keep it balanced, so that's going to be 60. And then we put our mass in. Again, this is the total mass, so 2 plus 4 plus 12 is 18. Okay, and our acceleration comes out to be 6.33. Trying to save a little space here. All right, so now I want to see if this system can actually do that. So now I'll look at the block on top, and I'll kind of do what we did last time. I'll think about just that block on the top, and I'll look to see, well, how much friction would I need in order for this block not to slip? Okay, and the amount of friction I would need, what that F sub F2 would need to be, would be 2 times 6.33, or 12.66 newtons. All right, well, let's see if we've got that. Okay, the maximum amount of friction is going to be mu times the normal force. So that's going to be my coefficient of static friction, the 0.4, and the normal force is the normal force right at this surface here. Okay, so that's just the 20 newtons. So that comes out to be 8. Uh-oh. Okay, we don't have enough force. We don't have enough friction. I need 12.66 newtons. I've only got 8 possible newtons, 8 or less. So this slips. So that means this assumption is wrong. And unfortunately, everything I've just calculated is wrong. Okay, so I'm going to have to kind of start over here a little bit and fix that. I'm going to have to treat these two objects as separate entities. All right, so I erased my board here because I've kind of got to start over. Now I know that it slips. Okay, I've got to kind of look at each thing separate. So let's start by looking at just the top block. Okay, so we'll look at the 2 kilogram block, and we'll say again that F is equal to ma. The only horizontal force on this is a frictional force, but now that I know it slips, then it is a kinetic friction, and I can calculate that directly. All right, so mu times the normal force equals ma. I know the value, or I can find it. So it's 0.1 times, and again, the normal force is just due to the 2 kilograms, so 20, and I'm just looking at the top block. I haven't really focused on any other part of the system yet. And so 2 is my mass, and I can find my acceleration. I'll call it acceleration top, so that I remember it's just for that top block. And this comes out to be just 1 meter per second squared. Told you I made the numbers work out nice. All right, so 1 meter per second squared. Now we'll take a look at the rest of the system, and I don't need to look at these 2 blocks as individuals because they do move together. They're connected by the string, and so now it's kind of like I have this mini ideal pulley system. The only things I got to keep in mind here is that I have friction down below, like we had a minute ago, but there's also friction from above, because this 2 kilogram block is sliding, and so it's going to exert friction on the top of the lower block. Okay, so I've got to include all of that now as I look at my 2 block mini system. Okay, so I have 120 newtons of force pulling down due to this 12 kilograms. I have friction due to, I'm just going to call it this. Okay, F sub F1 and I have F sub F2. Both of those are working against the motion. And then my mass, I'm going to put this in right away so I don't mess it up. The mass is going to be everything I've got in red. So it's going to be 16 times my acceleration. And this is a different acceleration, so we'll call it acceleration bottom. Okay. So on the left-hand side here, I'd have 120 minus, and these are all kinetic now because everything's slipping. So it's going to be 0.1 times, okay, and F sub F1 is this bottom, is at this bottom section. So all of that weight, the 60 full newtons, is pressing those surfaces together, and so that's what determines friction. And then on the top here, this frictional force, this F2, that is only due to the push between the 2 and the 4. So it's only due to the 20 newtons pushing down. So here I have 0.1 times 20, and that's going to equal 16 times my A bottom. And here when I go through and calculate A, it comes out to be 7. Okay, so that kind of makes sense, first of all, just to make sure we're thinking about it. 7 being greater than 1, I would expect that, from my perspective, it would look like that 2 kilogram block moves backwards, okay, because it's not moving nearly as quickly. Its motion is not changing at the same rate as that bottom one. And so from my perspective, it's going to look like that top block moves backwards, even though it's moving forward, but just not as quickly. So this is the acceleration, 1 meter per second squared of the 2 kilogram. And this is for the 4 and the 12. Messy, but done.